So this is one in a series of videos I want to make demonstrating the new 2 and 3D solver in OghmaNano. So if you click on New Simulation and Gallium Arsenide Demos, you'll see a whole series of demonstrations that use the 2 and 3D solver. And the demo we're going to be looking at today is the Gallium Arsenide 3D Defect demo. And you might ask why we're looking at gallium arsenide material system in this example. Well, OghmaNano has historically been used to model disordered materials such as organic materials and perovskites, but there's no reason why it can't be used to model other inorganic materials as well. So I thought I'd do some demonstrations on that. So once you've double clicked on that and saved it, you'll get this simulation window here, which pops up, and what you can see is, well, the first thing is a nice star field in the background, which is actually quite cool. This is actually the real stars all around the Earth rendered, and it just gives the simulation some nice perspective. Anyway, moving on, what you get in terms of electrical device is you get this structure. You've got 1, 2, 3, 4 layers to the device. So we can look at that in the layer editor, and we've got it claims it's air, but it's actually a contact. You've got your gallium arsenide. You've got your gallium arsenide p-doped, you've got gallium arsenide n-doped here, and you've got another contact here. And currently I've just, if we just make this a bit bigger, I've just set this to be, I've set it to not show as solid, so it's actually a solid object. So if we set that as a solid object, this will show you the structure a bit more clearly. So let's just undo that so we can see what's inside it. And what I put inside this diode, you might say, oh, what are these weird box structures inside it? Well, this represents a defect. So this could be, for example, a sort of defect introduced through sort of non-perfect fabrication, or it could be introduced, say, due to degradation in sunlight or some laser striking it, or something like that. But what they are effectively is just two cubes of different with different electrical properties to the main body of this device, and you can move these cubes around. You can sort of as you like, and set them wherever you want. So I just put them so they're overlapping, and I've really just arranged them to give us some sort of interesting 3D structure to show off the solver. So let's just look at the electrical parameters. So if we look at the electrical parameters, effectively we've got the gallium arsenide p-doped, the gallium arsenide n-doped, and with sort of sensible parameters for those, and we've got defect 0 and defect 1. And if we look at the doping of this device is in doping and ions, and we can see it's a linear doping profile from sort of here down to the centre, and then linear up the other way. So let's just run this and see what it does. Now it's a 2D simulation, no, well, it's a 3D simulation, so it's actually going to take a relatively long time to, well, it's quite quick, but it's definitely nowhere as quick as the 1D simulation. So you see we're taking about between 300 and 400 milliseconds per voltage step. We're slowly ramping up from 0 volts. We've got a little progress window here, so we're slowly ramping up from 0 volts all the way through 0.5 volts and up to 1 volt, which is where we're stopping. And once simulation gets past 10 seconds, it gives you a little time check every few seconds to sort of say how long it's been running for since the last time check. So, and there we go, it's finished. So what do we get? Well, in the output, the first thing we get is we get a JV curve, which is like unsurprising. And I think it's worth also just going back to look at the terminal and just try and understand this output a bit. So we've got two contacts. We've got a bottom and a top contact, and we're ramping the top contact from 0 volts all the way up to whatever it is, 1 volt. And this is the current on the output. And you can see the current sort of looks a bit lumpy, as it were. So it's got minus volt, minus current, positive current, minus current, positive current, minus current, positive current. And then all of a sudden, once the diode turns on, we start getting consistent exponential growth of this current. And the reason for that is it's just very difficult to solve the diode equations, or the sort of diffusion equations, when there's no current flowing. So effectively this diode is turned off and we're trying to solve it for 0 current, so that's quite difficult. So that's why it looks a bit lumpy. Here we get how long each solver step took, and here we get the error. So this is how accurately it solved the equations. You can see once we get up to sort of positive voltages, the error drops to minus 12, minus 10, minus 8. That's very, very good. That's excellent, in fact. but sort of at these lower voltages, it's sort of just -8, it's -7. It's struggling a bit. It's okay. Okay. Anyway, let's look at the output a bit more. So let's look at the snapshots, and this will tell us. Is effectively we can plot stuff about the device. Interesting. So let's open this up, and we get another copy of the device in 3D. But what we can do is we can add to it things like the conduction band. So here we put EC, and we can step through this as a function of voltage. The voltage is going up there, and we can step through this as a function of voltage, and we can see effectively how the voltage changes in 3D. So that's not very intuitive, but let's look at, the conduction band isn't very intuitive. Let's look at the current, because that's a bit more intuitive. Let's look at the electron current going in the Y direction. So we've actually got 3 currents. We've got 6 currents. We've got current, so electron current going X, Y, and Z, and we've also got whole current going X, Y, Z, and the X, Y, and Z is denoted by this little thing here. So X, Y, Z. So anyway, let's step through this. So we're now looking at the electron current, and you can see basically when we're starting off at, let me just try and move this. When we're starting off at low voltages, it's sort of bumping around a bit here. It's effectively because we've got no current flowing, so it's sort of this is numerical noise we're looking at. Then all of a sudden, when the diode switches on, which is about here, we start to get a very, very strong current flowing through our defect. And if we go to the top of our device like this, we can basically zoom, we can basically slice through our device vertically and sort of see how that current's flowing through our defect of our device. And as the current increases, it becomes very, very obvious that current's just basically our defect shorting our device out. And you can go back, and so let's for example, let's go and delete that defect. So we just delete that defect, and rather than running a simulation in 3D, what we're going to do is run it in 2D. So we're going to go to electrical mesh tab, and we're going to turn off the Z direction. So we can turn off the sort of dimensionality of Z, and we're just solving X and Y. So what we're now going to be doing is solving effectively just along here and down here. So if we run it, it's going to be a lot quicker, super quick. And what we can now do is go back to the snapshots, and we can start to get some more sort of intuitive pictures. So this is the conduction band as we start up, and you can see it's sort of a bit more obvious to understand the colour map. We can look at the let's just look at the charge density, so Qn3, and this is what happens to the electron density. We can add the hole density, Qp3, so we can effectively see how these parameters change in 2D. And if we really feel the need to project this into 3D, we can just click the 3D mode button, and what we can do is we can basically watch this in 3D. So here we can see the various well, let's look at the J. Let's get rid of that. Let's look at J N. There we go. There's JN. Let's look at this current in the Y direction. There we go. And the diode turns on, and then all of a sudden it's very strong current, I guess, going from one side to the other. And you can see the color bar there. So, and that's actually projection. You can sort of, if I put this on top, always on top, you can see that's sort of a projection of the value onto this. So what have I shown you? I think this is, it's a bit of not quite rendered correctly anyway. So what have I shown you here? Well, this is effectively a demo of simulating 3D devices, and also sort of odd asymmetric structures to really use the 3Dness of these simulations. Warning note I'd give is that all electrical simulations, whether in OghmaNano or any other software, when you start ramping up the dimensionality, you start getting a lot slower, and this is because as you increase sort of X, Y, and Z by 1, your number of points you're solving goes up by a factor of cubed. So 10 by 10 simulation is very easy to solve, like this one. 20 by 20 gets a lot harder. 30 by 30, you're going to be sitting there a long time waiting for it. And it's the same with any solver. It's not just OghmaNano. It's all of them. It's just how tricky this equation set is to solve. So yeah, final tips are, I would say go for 1D simulations if you can. If you need 2D, if you've got 2D effects, go for 2D. If you really need 3D, do 3D, but there's always that cost and increase in the dimensionality. So I hope you enjoyed that. That was just a little demo, and yeah, thanks for watching. So having just finished this video, I've realised I forgot to say one really important thing, and that is that if you go to the optical tab and you go to light intensity and set this to 1 sun, all of a sudden you get a lot of photons appearing on the top, and what this means is the light has been effectively switched on, and it's effectively now gone from a diode to being a solar cell. And it's not an optimum device because you've got this nasty shunt resistance here, and it's not been optimized in terms of thickness to be a solar cell, but nevertheless it is a solar cell. So if we go ahead and run the simulation with the light turned on, what happens is, so it simulates effectively the light propagating into the device as a function of wavelength using the transfer matrix method, and you can see you get this sort of very small photocurrent here, which is the device, so it's effectively a negative current, so the device is acting as a solar cell. So it's going to ramp up, so we're at sort of 0.3 volts, we're going all the way up to say 1 volt. And after that's finished, what we'll be able to see is hopefully we'll see a JV curve with some negative current, and that will show that we've got generation of power. So just give it a second to finish. And should I say, yes, I think whilst we're here, we'll say that you can change the solar spectrum by going to the light sources tab and selecting what sort of spectrum you want to choose. So there's a few already built in, like a CO2 laser and various other random lasers, but we're using M1.5 here. So it's finished, so let's now go and look at the JV curve. So it looks like a normal JV curve, but if we zoom in down here, you can see that we've got a negative current, so we've got a photocurrent there, and the noise there is effectively due to numerical noise of the solver, because it's a very, very small current. It's very, very hard to solve for, but nevertheless it is a JV curve that looks like a solar cell. So yeah, that's it. So thank you very much for watching this. I hope you enjoyed it. So yeah, goodbye.